So this video is more of a summarization of all the different tests for convergence and divergence that we've gone through. So this is kind of a good review for you and a game plan for what do I test first? What do I look for? Things like that. Okay, so I'm just going to walk us through the different strategies for testing for convergence of or divergence of infinite series. Okay. So the first test that I like to do, and the reason I like to do this test is because it's the fastest. And that test is the nth term divergence test. Okay, this one's definitely the fastest. The only thing that this test is going to tell you is if a series diverges. And how do we do this? All we have to do is look at the an and take the limit as n goes to infinity. And if that thing is not equal to 0, what that's telling me is that the series, at some point, you're going to be adding some non-zero number an infinite amount of times. And no matter what that non-zero number is, you add it an infinite amount of times, you're going to diverge. Okay? So if, however, whenever you run the test and you get an limiting to 0, then the test fails and you have to move on to another test. Okay? So the next test that we run into is the geometric. The geometric series, you can write it in this form or this form. The only difference between the two is where we start with our n. Okay, so that's really the only difference there. And it might be good practice, like if they give you some n to start and try to convert it back to an n equals 0 or something like that. So like if, maybe if I gave you some, n equals 2 to infinity of a r to the n, and I said, I want this to start at 0. Well, what would you have to do to make this start at 0, right? Well, if I plug a 2 in here, that gets me a 2 there. Okay, so if I'm going to make this start at 0 instead now, I'm thinking that first term as an r squared, well, now I'm going to need like an r to the n plus 2 to make that work, okay? So that right there would give you the same series. So just an idea. You're not having to do that right now, but potentially you could run into an issue. When we talk about Taylor and Maclaurin series, we'll talk more about that. The big thing to remember with the geometric series is the first term. The first term, that is my A, okay? So if I know that the geometric ratio, so that thing that we're raising to the n power, the r, an absolute value is less than 1, then I know this is one of the few series that I know what it actually sums up to. It sums up to a over 1 minus r. Now, you can think of this as the first, okay, so let me rewrite that. So the first term divided by 1 minus that ratio. Okay, so the first term, so it sums to the first term divided by 1 minus the common ratio. It's very important that you understand that that's the first term in my sequence, okay? Whenever I plug in that first term, n equal 1 here or n equals 0 there, that first term is your A, okay? Can't stress that enough. Now, if r, the absolute value, that geometric ratio, what I'm multiplying each term by to get the next term is greater than 1, then the series diverges. I mean, it makes sense, right? If I start, my first term's like 1, and then to get the next term, I multiply by 2. That gets me 2. To get the next term, I multiply by 2 again, I get 4. And the next term multiplied by 2 again, I get 8 and 16 and 32. If I add these up, that's for sure going to diverge, right? So that for sure diverges. So remember the common ratio, this is what I multiply by to get the next term. So the only thing you have to do to get the common ratio is divide two consecutive terms. Okay, so you divide that an plus 1 term by the an term. So that becomes an plus 1 over your an, which is your common ratio. And if that common ratio is less than 1, then you know that the series converges and it sums to this value here. I hope this looks familiar to you. You should be thinking, that almost kind of looks like, I don't know, maybe the ratio test, right? Imagine that. Okay, so geometric, this is one that we know what it sums to. Telescoping is another one that we know what it sums to. Okay, so a telescoping series is very important because we actually can figure out what the sum is. Now, how do we do this? We look at the nth partial sum, Sn, okay? And then we take the limit as Sn goes to infinity. Now, to get that n partial sum where I can write it and I see how I have it split up into two terms like this. Typically, partial fractions. So, typically, partial fractions is used. Or you could use some log properties depending on what's going on. Remember, like if you're going to do a log property like log of A divided by B, that's like what? That's like log A minus log B. So that's what I'm talking about with property there. And then multiplication, log A times B is log A plus log B. Okay? So that's what I mean by log properties. Partial fractions is probably what you're going to run into, but just in case you ran into log properties. And then you would write an as some difference to help you figure out, okay, I can write out my terms, kind of like that problem we did where, the first term survived, but this term right here got killed by something in the future. And so that means that the first term gets killed by something in its past, and the second term gets killed by something in the future, first term gets killed by something in its past, and then all you're left with are two values. You add those two together, and then you take the limit as n goes to infinity, and you get what it actually sums to. So we can find the exact value of a series for the geometric and the telescoping. Okay, so if I ask you on your test or in any question, I say, find the sum of this infinite series, then you should hear ding, ding, ding in your head. You should be thinking geometric or telescoping, okay? Now, with the p-series test, this is my next go-to. So I'm going down the list and like in my head, this is the list I go through every time I look at a series. I always check the easiest thing first. That's nth term divergence test. If it doesn't go to 0, then I know it diverges and I'm done, okay? So those fail, then I run into the geometric. And geometric doesn't work. I'm not asked to figure out the exact sum. I don't worry about geometric or telescoping. So now I'm going to the p-series. Why am I going to the p-series next? Well, I think p-series personally is pretty easy. All we do is we look at the power on the exponent for that polynomial in that denominator there. If p is greater than 1, then we know the series converges, okay? And if p is less than or equal to 1, then the series diverges. So those typically end up being really easy. I like the p-series when I'm going to run with the limit comparison test or the direct comparison test. Why? Because when you run the limit comparison test, okay, when you do this test, not only do you need to make a guess on what you think AN is going to do, but you got to know what BN is going to do. And so you pick a BN that's either it converges or diverges by p-series, or it's similar to some geometric or something like that, okay? Or maybe in rare cases a telescoping. But typically geometric or p-series is a good one that I compare with my limit comparison test. Personally, I like to take limits more than I like to do the direct comparison test, but whatever floats your goat on that one. The rule about the limit comparison test, really what you got to watch out for is when you take that limit, you get something that's positive, okay? And it's not infinity and not zero. So I can't have my limit equal to zero or infinity, okay? So as long as it's some positive number like, I don't know, a half, 15, 32, 1, whatever, as long as it's some positive number greater than zero and it's finite, then we're good to go. So if that's the case, if you get that, then either both a_n and b_n converge, or if you picked a b_n that diverge, that tells me a_n diverges. Okay? So you want to pick a b_n that you already know. And so geometric, p-series, these can work, but sometimes it might be a little trickier. Okay? Now, if you run into a scenario where you do your limit comparison test and you end up getting, you pick your b_n and then the b_n and your limit gives you 0 or infinity, then, the test, it just fails at that point, okay? So at that point, we would run into the direct comparison test. And so with the direct comparison test, what you're thinking about doing, okay? If your goal is to prove that a_n converges, that's the goal, okay? You want to prove a_n converges. That's what you think. You're looking at it, you're thinking, man, this thing looks like it's going to converge. It definitely looks like it's shrinking fast enough that this series, the sum, is going to converge. Then what you have to do is you've got to create a b_n. You make one up that converges, but that b_n is greater than the a_n you're trying to prove converges. And if you can do that, then you conclude that the series a_n converges, okay? Now, very different is if you're trying to prove a_n diverges, okay? If you're trying to show that a series diverges, you need to create some b_n such that the b_n is smaller than the a_n, but b_n diverges. And if b_n diverges and it's smaller than a_n, then that forces your a_n series to diverge, okay? So you have to make sure that you create some b_n that diverges and is smaller than the a_n's, and then therefore it pushes your a_n up, okay? Now, the integral test, what do we have going on here? Well, the integral test is a pretty nasty booger, okay? So this one's like pretty far down on your list. All right, the integral test, we turn a_n into a function, okay, a function of x, all right, for some, x greater than 1 or whatever number we need to start at, as long as it's some finite number, we're good to go. Because maybe you have some function and like it increases, but then at some point it starts decreasing from then on. So maybe at like x equal to 4, maybe at that point, now the function is continuous, positive, and decreasing from then on. And if it's some finite amount here, then that is okay, all right? Because what you can do is you consider the infinite series from that starting from this point, so maybe n equal to 4 here to infinity of whatever your a_n is. And then all of these before, that would just be n equal to 3, n equal to 2, n equal to 1. If you're adding up a finite list of numbers, okay, and none of those are infinite, those outputs of your fn's, okay, remember we're making a function that represents these a_n's, right? then you know the sum's going to be finite anyway, just from basic arithmetic. Okay, so what does this say? The only time you can use the integral test is if you can show that f of x is continuous, positive, and decreasing. That's a lot to prove, so that's why I try to stay away from it unless it's absolutely necessary to use it. And if this is true, though, if I can show that to be true for f of x, then what can I say? Well, if I compute the improper integral from 1 to infinity or 4 to infinity, like our example here, whatever we start at, some finite number out to infinity, and that thing converges, then what do I know? The series from 1 to infinity also converges, okay? And then same, if the integral diverges, then the infinite series diverges, okay? But what I want you to note, and something that I stressed in the lessons, was that just because it converges doesn't mean it converges to the same number, okay? So the same number of the integral, all right? So you think about it like the integral, I think we did this one, the integral 1 over x squared dx from 1 to infinity was equal to 1, but the sum 1 over n squared 1 to infinity was equal to like pi squared over 6. So they both converge, but they don't equal each other, okay? All we know is that they are both convergent, all right? Now, the alternating series, this is whenever we're swapping between positive and negative, positive and negative. We're alternating. We've got some sign switcher. I like to say, this is my sign switcher, -1 to the n. So what we're looking at for the alternating series is this an part here, okay? So that's how we've defined it for our alternating series. We want that an part to be positive, right? Okay. Now, to show this, okay, we need to start with some assumption. If our n starts at 1, we can assume for n greater than or equal to 1, because n equal 1, n equal 2, n equal 3, n equal 4, n equal 5, so on, right? Now, what do I do to use the alternating series test? I need to take a limit. As n goes to infinity, I want to see where the sequence converges to. Now, sequence converging versus a series converging are two different things, right? So if I take the limit of the sequence and I get 0, that's great. That's the first part that I have to satisfy. The second part I have to satisfy, okay, now you can do this second, right, is that my terms are non-increasing or decreasing. Each term gets smaller and smaller and smaller. Okay, so I'm non-increasing, so I'm going down, okay? So you can write this by actually writing it out, right? If I have an is 1 over n, then an plus 1 is 1 over n plus 1, and you would need to show that this is true there. And so you start with what you want and then work till you get to something that you know is true, right? And then go backwards and write out your steps, and you got it. If you can prove this and you can prove this, then what does that tell you? That tells you that the series converges. Now, it technically converges, it converges conditionally. We'll talk about that in just a little bit. Okay, so the ratio test. Ratio test is one of my favorite tests. I love the ratio test. It's very similar to the root test. The ratio test, literally we are looking at the ratios of the n plus first term divided by the nth term in absolute value. And if that ratio is less than 1, then the series converges absolutely, which is very powerful. If that ratio is greater than 1, then that series diverges. And if it equals 1, then the test fails. Okay, so you must do something else, all right? So ratio test and root test are very similar. Like I talked before, this right here, this what's going on here is kind of coming from the geometric series. If you go back to the geometric up here, you know, we talked about dividing through, okay? So we talked about dividing that n plus first term divided by the nth term and being less than r, absolute value of r. So very familiar, hopefully, to you, okay? So ratio test, that's definitely a good test to run through. The root test I didn't have on my little sheet, but I'll write the root test down since we've got it. The root test, okay, so root test says if the limit as n goes to infinity of the nth root of the absolute value of an is equal to L is less than 1, then the series n equal 1 to infinity of an converges absolutely. All right? If, and so second part, if, and then the limit as n goes to infinity, absolute value of the nth root of an is equal to L, which is greater than 1, then the series diverges. Okay, looks very familiar with this. Less than 1 converges absolutely. Greater than 1 diverges. So this is very familiar flavor. If it equals 1, then the test fails. So let me, oh my goodness, I'm gonna get it on this track. Okay, so if this is equal to 1, then series, then I'm just gonna say the test fails. Okay, so the test fails. So that is the nth root test. I would use this one if I see something powers to the n, okay? The ratio test is really useful. It's good to use when you see factorials or, you know, when you have powers to the n here. I have, you know, I didn't put the root test in there because truly, like, the ratio test can help us out there. And any problem that the root test can work through, the ratio test can also be a good help for. There might be some examples you could come up with that might stump it, but typically, on the whole, usually the ratio test can take care of anything that the root test can take care of, okay? But, you know, there might be 1 or 2 types of problems that it couldn't take care of. But this is just a summarization, you know, more of a 30,000 foot view of all the different tests that we've run through so far. So hopefully by seeing all these, you know, maybe it kind of gives you a better perspective and, you know, gives you some ideas of what you would do when you're looking at each problem and you're like, man, what should I try to do, right? Now, there are ways to get around, like if you do the limit comparison test and you get 0 or infinity, we talked about those in other videos. And so, like, if you can't find one where it's, you know, where every time you take this limit, you either get whatever you're comparing it with, it gives you 0, if it gives you infinity, then there is a way around this. And I suggest that you go watch that video on the limit comparison test. Okay, so the limit comparison test video will show you what to do in these scenarios. Okay? All right, guys.